Hi, caro Pettirossi, voratomi per la pace. In May 2013 we started a cycle of interviews by having a very special guest, Dr. Edward Calabrese, Professor of Toxicology at the University of Massachusetts Amherst. Today we are honored to have him again for another Skype chat. Professor Calabrese, thanks very much for this opportunity.
My pleasure.
We read that in 2015 you wrote to Science magazine a very detailed letter citing the fraudulent behavior of the BEIR and the BEAR committees. Can you please tell us about it and whether there have been consequences?
Well, this has been a very interesting, exciting, and frustrating endeavor. Um, the the material that I published has been very extensive and very well documented, indicating that the BEAR 1 committee of 1956, in my opinion anyways, committed scientific misconduct in their report, and that they misrepresented the scientific record to support conclusions that were tied into their ideology, trying to support the adoption of the linear non-threshold dose-response relationship. Now, what I did was to contact the editor of the journal Science, Marcia McNutt, who has recently become the president of the U.S. National Academy of Sciences. Now, I informed Dr. McNutt of my allegations, provided her with the published material that supported those allegations, and I requested that she initiate a process that would result in consideration to have the 1956 paper that was published by the National Academy of Sciences BEAR 1 Committee in Science, have it retracted from Science. Essentially, because of falsification and fabrication of the research record, just as you would do with other papers that you had discovered had committed falsification and fabrication. And so this led to a series of email exchanges between myself and Dr. McNutt. And basically she came up with 4 or 5 reasons why she initially didn't want to do this. And then I answered her 4 or 5 questions, which I felt I easily answered her questions and showed why each of her objections was not valid. Then she went to she then wrote me back saying that she had expressed in general terms this situation. I don't think she mentioned necessarily my name or the specifics, but in general terms, to a group of very prestigious scientists, and talked about would they be comfortable in retracting a paper in which they couldn't defend themselves. So like she set this thing up as a straw man, so to speak, because knowing that all the members of the BEAR 1 committee had died. And so therefore my allegations of the BEAR 1 committee could not be rebutted, refuted by any member of that committee, because they were all dead. And so these scientists, I'm not sure how she explained this to them, but none of them felt that it was fair to retract a paper that you couldn't defend yourself on. But I don't think she explained the situation. The bottom line was that she kind of treated my very serious situation in a way to trivialize it. And ultimately, then you have to also understand this, at the time that I made the request to her to retract this paper, she had been nominated, and in fact was the only one nominated, and her name was on the National Academy of Sciences website as having been nominated to be the next president of the U.S. National Academy of Sciences, and she should have recused herself from making the judgment on my request to retract the paper from that was published by a National Academy of Sciences committee. She had a clear conflict of interest. And yet she did not recognize or address, or nobody told her. But you would think that the editor-in-chief of science and the president-to-be of the U.S. National Academy of Sciences would have the experience and the judgment that could actually see a potential conflict of interest. And yet, apparently, she didn't. To me, it's really very disturbing that one in that sort of a position can be apparently blind to this most obvious, I think, fact that almost anyone else could see. And so what happens is that the people in power continue to stay in power, and they continue to blunt legitimate attempts to have a fair hearing when you challenge a position. I don't know actually what else one can do other than, you would think that there should be some sort of a storm within the scientific community when you have such blunting of legitimate opposition and such power that's rested in the hands of so few, in which there is self-interest operating in so evident self-interest. So in effect, my attempt to go through the process, legitimate process of trying to seek out the retraction of this paper, in which I believe that the evidence is really strong that there was a scientific misconduct, and I'm not saying that they should believe me. I'm saying that they should set up a committee to see if my allegations are right. The way you would normally set up when certain serious allegations are made. I mean, I could be wrong, but I don't think I'm wrong. And I'd say it's up to other people who are unbiased to make the recommendation to the editor, rather than her, who's not a radiation scientist and not a historian of science, to make a judgment that she did. So I wasn't pleased, and this fight's not over yet, and we'll see how it all goes. And there's more, and I can tell you there's more new things to be published along these same lines. So this story is not over. It's an evolving historical unfolding.
Does anyone share your position, or are you completely alone in this kind of crusade?
Oh, I think that a lot of people have been convinced to the historical truth of what the papers say. And the reason for that is that the documentation that is cited in the papers is very detailed and is actually pretty easy to understand. And the reason why it's easy to understand is that you're actually following the conversations of the people who are in the committee itself. They actually provide the contradictions and the falsification in their own words. And it's not that I have to make it up or I have to infer or that I have to extrapolate, because what I have actually uncovered is a series of memos and historical documents and exchanges between scientists, which in their own words show their essentially agreement to cover up information that they had, to not represent that information, to misrepresent that information, and to do this to enhance their political, ideological goals. And so I think that the difficult thing here is that each one of those members of the U.S. BEAR 1 committee, they were all outstanding gentlemen. I mean, career-wise, several Nobel Prize winners, major leaders in the academic world or governmental world. all serious leaders, people of tremendous accomplishment, but as it turns out, they all had a flaw, and I guess everybody has flaws, and nobody's the perfect person, but this was a very serious issue, and as it turns out, I believe that that this was a serious failing, not just by one person, but by an entire committee. I mean, you might look at certain people as the leaders of the committee, but in the end, the group voted. It was very interesting. You just can't blame the chairman, or you just can't blame an influential person or two, because they actually took votes, and they actually knew what was going on. It's not as if somebody went to the bathroom and they missed the vote. They were all engaged in this. So I feel good about the science side of it. I've been challenged on this. I've been challenged on the facts by multiple people, and the facts have withstood the challenges. So I feel good about it. Tell me where I'm wrong, and I'll change my opinion. But I believe I'm following the facts. So that's tied into BEAR, the BEAR 1 committee. Now I have to tell you that in terms of BEAR, I have new information that is coming forward in terms of I'm going to call it BEAR 1, which was published in 1972, and its impact on subsequent BEAR committees. And I have a manuscript that is in draft form. It's actually now being reviewed by friendly critics, so to speak, before I consider sending it out for peer review. But it will essentially bring the issue of LNT and problems with how it was dealt with to much more modern times. I'll wait to get the criticism from my friendly critics, so to speak. I typically send things out to about 10 people before I submit them for publication, hoping that they will severely criticize me before I make a fool of myself sending a paper out. Pass peer review well, but I suspect that I will be, and these are high level scientists who are very competent in the area of radiation, genetics, and related material. So it's so that's this manuscript's been out for about 5 or 6 days. I'm waiting to get some feedback by the end of this week, and then once I get my processes, once I get the first set of reviews, I'll clean them up, make them better. I'll send them out to a new set of people, go through the same process 3 times, and then see how my confidence is with the paper. If I'm comfortable with it, if I am, then at that point I'll consider sending it out for review to a regular journal, which I hope will take place probably by the middle of July. Just all this stuff, all this takes time, and I realize the stakes are high because I am making some significant challenges, and so I want to make sure that I do it correctly, and that I'm open to the criticism from knowledgeable people before I actually get into the peer review process. Even more criticism. So, but this next paper will deal with activities within the BEAR setup as compared to the BEAR setup. It becomes much more recent and almost to the present time, pretty much to the present time. So it's going to be interesting. It's going to be as it's going to be significant if it makes it all the way through. Yes.
By the way, LNT, can you tell us what's the difference between the LNT model and the hormesis theory?
The difference between the LNT and hormesis. Okay, well, there's a world of difference between the two, and that in terms of practical situation, the LNT is really based upon a belief that that the response is directly proportional to dose, and that even if you can't measure it, this relationship will still hold, and that you will have biological effects down to a single ionization or a single molecule, and so it's really far outside of what you can measure, and but yet belief systems are based upon this, and I also have to say too that when people are studying radiation-induced damage, it's not uncommon for people to say they're studying at low dose rates that could be, I'm going to say probably 3,000 to 5,000 times above background, and they will call it very low dose rate, 3,000 to 5,000 times above background, and so the use of words is very troubling. When to a normal reader, you always keep having to take a look at, well, exactly what dose rate did they do? Why did they choose this dose rate? Was it due to the insensitivity of their own instrumentation and biological system? Why would anybody who's talking about low dose rates be studying, doses at 5,000 times background? And that's okay to study at those doses, but it's usually the papers are never really placed into a much broader context. But so the LNT is really making the assumption that the relationship is really unimpacted by biological system. It's just a more of a functional physical system with dose response relationship being essentially directly proportional to the response, directly proportional to dose. The hormetic system is actually very different. It's very biologically based. It takes into account that the cell and the organism, well, they actually are part of the equation here. When they get hit, they kind of try to protect themselves. They actually don't take it sitting down. It's kind of like if somebody punched you in the nose. Well, you'd probably respond to that. You might run away, or you might punch them in the nose. But there would be a biological response. And in the case of the hormesis, when there is damage that's induced by a chemical, toxin, or ionizing radiation, the system is alive. The system is alive because of, guess what? It can repair itself when it's damaged. It actually needs to be able to repair itself to live and to go forward. So when you are hit with something that damages the cell membrane or an organelle or the DNA or something within the process of what makes up life, I think it's really important to assume that in fact that highly evolved systems would have developed various and complementary and redundant repair systems that would allow them to rapidly repair damage and clean out the damaged material, replace it, kind of not unlike a person who owns a home. When a window is broken, you fix the window. The door is broken, you fix the window. You have a flat tire, you fix the flat tire for your car. I mean, these are physical things that you can call them living because we're living within them. Same with our body. This is so evident in terms of you cut yourself and it heals, things of that nature. So the idea that biologists, it's very hard for me to understand how biologists could have grown up and adopted an LNT which is a non-repair concept, and accept a non-repair concept when they are biologists. And it's actually rather interesting that that in fact the maybe it wasn't the first, but about the first time when the concept of repair took place was in fact, I mean, it's very interesting to me that the concept of LNT and showing, this linear dose response, it was really developed by Hermann Muller. Hermann Muller got support for this in his own research because the model that he selected were a mature spermatozoa. So he's studying males, and he's studying males in reproduction, and he's using this, sex-linked survival issues for his endpoints, and he's studying mature spermatozoa. Now, it's very interesting that in a fruit fly, the end process of the reproductive period results in a mature spermatozoa that is functional for a few hours, 4 or 5 hours. During that time, when you're getting to this point, the process is squeezing out of the spermatogonia on the way to the mature spermatozoa. It's squeezing out cytoplasm and essentially making the mature spermatozoa be basically a carrier of DNA for reproductive purposes, and it essentially loses all its DNA repair capacity. So what in effect Muller was studying for his mutation was in fact a biological model that actually had essentially all of its DNA repair removed from it. All our somatic cells and our reproductive cells up through the spermatogonia and so forth have a full complement of repair capacity. And yet what happened is, with the Ames test, one reason why the Ames test was so sensitive for mutations was that the Ames test with bacteria had its DNA repair capacity removed from itself. Right? It was molecularly removed, and that's why it was so sensitive, and why the results often showed a linear dose response. It didn't represent real life as we would kind of know it. It represented an extreme sensitizing of that. And what the mature spermatozoa is, in effect, is actually a reproductive mimic of an Ames test that has actually the mature spermatozoa naturally losing its DNA repair capacity, whereas in the Ames test it was artificially taken away. But they're designed to show very sensitive responses. Now, how in the world anyone could have gone from this situation to generalizing from mature spermatozoa to accepting LNT for somatic cells? I mean, it really has to fail the exam. And this is what major committees did back in the late 1950s, and then being adopted as we go forward. It actually made no biological sense, and these people who were biologists acted in a very non-biological way of thinking, and this is, I think, where you contrast the LNT viewpoint versus the hormetic viewpoint. The hormetic viewpoint actually takes into account the biology, takes into account that the system can process, and that system can repair, the system can overcompensate. It really looks at biological systems and integrates within those biological systems, whereas the LNT model is actually, for the most part, a very non-biological model. And people persist in, biologists persist in embracing a model that lacks biological realism. So I hope that kind of compares and contrasts the LNT versus the hormetic. So the bottom line with the hormetic is that you're not going to have a linear dose response relationship. that as you begin to incorporate elements of repair and other components of the adaptive process, you really get a sharp decline from linearity, and a lot of evidence shows that in fact some of these repair processes actually are able to, once they're induced, they themselves impact even the natural or the spontaneous mutation rate, and actually you get a dip below background, and that's really what is producing the hormetic dose response, this net benefit that we might see. But really, the hormetic response, the adaptive response, is really going to lead to both thresholds, and it's going to lead to actually even hormetic responses or benefits. And I think this is why we see it so often in the literature when you actually begin to look at it, and why there are so many exceptions to the LNT, and why the LNT was, as I said, based upon a system of heightened sensitivity, which had removed essentially all its adaptive capacities. And even me, who tends to be very strongly supportive of hormesis, I could understand that they would get a linear dose response in a mature spermatozoa that had its DNA repair removed. And that's not really much of a surprise. And even there, I would hold out the possibility that even in that situation, there are still elements of residual repair processes that are still present, although probably in an extremely diminished capacity. So that if you really were to take a look at truly very, very low doses, with even to spermatozoa, you would probably see deviations from linearity there as well. That's a research question, should be studied.
In one of your articles, you talked about the hormetic database. Can you tell us more about it?
Yeah, the hormetic database is, well, I actually have several databases. I have about 4 hormetic databases. They were designed to answer different questions. So they serve different purposes for me. One is a very large and general database, which actually is added to every single week, so it grows and grows as we find more things. And there's not a week that goes by that the hormetic database doesn't get added to. I'll put it that way. And that's actually, this database was very significant for me because it taught me a lot about hormesis, actually. Because what it did was it showed me, first of all, how wrong I was in my initial conception of what a hormetic dose response was. And I had some experience with it, but very limited to my research model in the laboratory. What the hormetic database did for me was to take a look at thousands of other studies, many thousands of other studies by other people with other models, other endpoints, other inducing agents, and then looking across this broad spectrum of findings and looking for patterns and consistencies and generalizations possibly. And to me, the most significant aspect of this was for me to learn that in general, the hormetic dose response is actually a very modest response. It's a low-dose stimulatory response in which the magnitude of the stimulation is usually not more than twice the control value. So if you were to try to increase the memory of a little mouse with a drug and it responds hormetically, you might be able to increase it by twofold. But generally speaking, it's usually even only by about only 30 to 60%, very modest, very hard, and that's what makes hormesis very difficult to study, because if you spend a lot of time in the laboratory and you look at the variability of your biological systems, you know that they're going to bounce between 5 and 20% on a daily basis. And so if you have an increase by 25-30%, you have to be sure that the increase you see isn't due to just chance or normal variability. And what it really taught me a lot was that you have to have very strong study designs, lots of doses in the low dose area. You have to have studies that you can replicate. And then ultimately, you have to come up with mechanisms that allow you to understand how this takes place. And you have to block those mechanisms so you can block the hormetic response, the whole package. And the interesting thing over time is that we've achieved these goals. And when we started with the hormetic database in the late 1990s, we had a lot of evidence of descriptive findings. By 1990s, I'd say 13, 14 years later, there's now hundreds and hundreds of studies which show demonstrable mechanisms for hormetic dose responses at the level of cell receptor, cell signaling pathway, very diverse sorts of biological systems. And the interesting thing, and that is that this might seem hard for anybody to get their hands around this, but we might have just dozens and dozens and dozens of hormetic mechanisms, regardless of the mechanism, how diverse it is and different system it is. Independent of the mechanism, the hormetic dose response has still the same quantitative features. It's actually pretty hard to understand that biologically. Is it why should hormetic responses in a bacteria, in yeast, in algae, in fish cells, and plants, and all the way up through all the mammals and everything, and all the different cells, they actually have pretty much the same quantitative features of that dose response. That's what emerged from our hormetic database, and it began to. And the other interesting thing is that you see this occurring in when you first stress a system, and then you have response to the stress. But you'll see this in an unstressed system under just normal developmental processes taking place, and this led me to some, I think, deeper insights into what hormesis was, and for me, and that was that hormesis seemed to me to be a system of biological resource allocation, in which you had a limited amount of biological resources, and you had to allocate, like a parent allocates an allowance to a child, to a large family, that you can't spend all your money on or all your resources on this dose response or that dose response. You're actually managing millions of dose responses all at one time, and yet you need to have flexibility. And the hormetic response is actually allowing for upregulation, but only a limited amount of upregulation. And as it turns out, I think that it's allowing for an upregulation of about 30 to 60%. And that's why I think you see this hormetic stimulation, and it actually ends up describing what I believe are the limits of biological plasticity. And hormesis is actually integrated into that concept of biological plasticity. And so I think that it sounds really strange, but I believe that our long time exploration of the hormetic dose response actually has led to some really fundamental understandings of biology that somehow slipped through the hands of 20th century scientists, and it was as a basic biological phenomenon with profound implications. And the fact that you have this limit of 30 to 60% within, and I believe constrained by the limits of plasticity, this affects essentially how much gain you can expect to get out of drugs that are increasing biological performance. Drugs that for example, designed to increase memory. Drugs that are designed to strengthen bone. Drugs that are designed to grow hair. Drugs that are designed to perhaps extend longevity. They're all going to be constrained by the limits of plasticity. They're all actually going to be evaluated within an hormetic context. And it really affects, I'm not sure big drug companies really understand it, but this really will affect how they design their clinical trials in terms of statistical power, sample size, things of that nature. It's really, it really drives that operation, and it also explains why how difficult it is to get drugs through the clinical trials, because essentially there's a lot of, in human terms, there's a lot of background variability. Trying to pick off a 30% increase and differentiate that from background variability is very tough, and I think that's why a lot of drug companies have seen great potential studies within animal models fail the clinical trial just because of this, because of the limits of hormesis of this only 30 to 60%, and why they tend to go more towards what I'm going to say, trying to target the drug to personalized medicine, because that way you're not getting it blended out by human heterogeneity and other kinds of factors. So the hormetic concept is very broad with its implications. It touches radiation very, uniquely, but it's also touching the rest of biology and the chemical world as well.
I have two questions on what you just said. First of all, how do you detect the improvement of the memory in a mouse, and why isn't it possible to do such experiments on humans, for instance, at this stage?
How do you detect the
memory improvement in a mouse?
You have essentially various types of memory retention tests. It's doing different maze runs or remembering of certain colors or certain schemes. There are a vast range of procedures in which you can measure the improvement in memory in a mouse and rat, actually. And it all goes back to probably the mid-1960s. People, most pharmacologists back up until the mid-1960s did not believe that chemicals could actually be used to improve memory. And then some graduate students at the University of California at Berkeley, they were working with smart mice and dull mice, and they wanted to see, and they believed that the reason why, they didn't know, but they hypothesized that maybe smart mice had more acetylcholine in their synapses than the dull mice. So they attempted to slow down the hydrolysis of the acetylcholine, and they wanted to build up levels within the synapse area. And what they ended up doing was they made the dull mice smarter, and they made the smarter mice even smarter. And then what happened is they eventually built it up too much, and both smart and dull at too higher doses, you might say, became too excited, and their learning actually broke down. So there was an optimal region, and their initial papers were rejected by the journal, and they went back and they fought through it, and they eventually got this in, and eventually it led to the development of Alzheimer's drugs that we have today. And all of those drugs, they follow an inverted U-shaped dose response. Every single, these 6 or 7 U.S. FDA drugs that are approved for the relief of Alzheimer's symptoms, all follow in the preclinical trials, the animal studies. They all follow an inverted U-shaped dose response, also a hormetic dose response. So that's on the mice. What was the second part of the story?
The second part of the story is why isn't it possible to test such things on humans?
I don't think it's impossible. I think that you have to test them on humans. It's typically, they may go from mice. They probably at the same time going from mouse in vivo to human in vitro. Eventually, these agents have to be tested in some framework within the human domain. Typically within a clinical trials. That follow ethical and efficacy protocols, but yes, this is critical. That's a critical component to the process.
Okay, then next topic. Please explain us the mechanism leading to an improvement of the organism by means of hormetic dose response.
Okay, mechanisms and hormesis. I've kind of alluded a little bit to it, but in the last 10 years, at least, there has been a real revolution in molecular biology, especially with regards to uncovering cell signaling pathways that mediate a whole host of biological responses, critical biological responses leading to adverse effects, biological responses leading to adaptive responses, and how they interact with each other. And the tools that allow you to dissect these pathways and how the pathways link to receptors. Now, I'd have to say, tied into this is that people are searching for complete pathways and complete mechanisms, and generally speaking, what I have found is that most investigators who get involved with hormetic dose responses and who have been successful have typically identified a receptor or a family of receptors or grouping of receptors that are necessary for mediating the biphasic response. They may know it at the receptor level. Then they get a little bit deeper. Then they have an idea as to what pathway this receptor is activating. So then they can go and then they can block that pathway. And then they can say, oh, that might also then block this. So then they may go deeper into a second pathway or a third pathway. And ultimately they're looking to get to a switch. And that's really what they're trying to do, is they're trying to find, is there, what actually causes this switch to be turned on and turned off, and what are the pathways that lead to the switch? I would say that in my experience, I have about 1,000 hormetic dose responses now, in which I have evidence for receptor and pathways which mediate hormetic responses, and blocking of those receptors, blocking of those pathways, you will shut down the hormetic response. You remove those inhibitors, hormetic response comes back. In only about a handful or two of this 1,000 examples have people come very close to switch. And so there are many labs throughout the world that are trying to tie every single detail down to pathway recognition, pathway detailing, every step in the pathway to ultimately a switch, complete characterization of a process. And so, but as I said, the near complete aspect is really a handful of cases. But as I said, I have 1,000, and there have to be more than that, in which the investigators, for the most part, they have a partial, a clear partial hormetic mechanism, and these mechanisms involve many different pathways, many different receptors. Sometimes the mechanism doesn't even involve receptors. It involves other vehicles to operate the mechanism. It's very complicated, but in the last, as I said, the last decade, there has been one of the big criticisms of hormesis 15, 20 years ago was that lots of examples, but we need to have mechanism. And it was a very common statement that toxicology worships at the altar of mechanism. And unless you have a mechanism, we're not going to really accept what you have to say about something. And that was profoundly affecting the acceptance of this within the toxicology world and pharmacology world. In the last 10 years, that objection has really just been washed away. And there's more evidence supporting hormesis than one could imagine if one actually takes a look at it. it's very, so that's pretty much the best I can do along those lines, or at least my mechanism.
Can you tell us what kind of substances are used to test the hormetic dose response and the criteria used to choose them?
Okay, what substances are used to test hormetic dose responses and criteria? Well, it's really in the mind of the investigator. There could be anything, a whole host of heavy metals if you're interested in heavy metals, from lead, cadmium, mercury, arsenic, whatever, to vast arrays of pharmaceutical agents, to a lot of people who use, cellular agonists, things like oxidative stress compounds. I would say there's the range of inducing agents is really just limited by the creativity and interest of the investigator. Hormesis is found right across the board, from what I can see, anyways, in terms of the chemical world, the chemical classes, and so I actually don't think if someone were to it doesn't make any difference actually what they're studying. There's a reasonably good likelihood that the chemical that you're working with today will actually in a hormetic response in a system. But also criteria that you use. Well, my criteria is really built around dose-response relationship, and that dose-response relationship means, and this is very important, you have to actually understand your biological system. You really have to understand the variability for the parameter that you're interested in measuring. People today, they measure a couple things. They measure integrative endpoints, and they measure signaling that leads to those integrative endpoints. The integrative endpoints can be, it could be as simple as cell proliferation. It could be memory. It could be a behavioral thing, a memory. It could be longevity. Those are all integrated fecundity. A lot of different integrated parameters, and you would study those within a dose-response relationship. But the investigators today, they also have to try to understand how that increase occurs at low dose, or their parameter of interest, and so they have to understand the mechanism. And actually, in my paper on hormetic mechanisms that was published in 2013, I spent a lot of time taking a look at pathways and signaling and the magnitude of the signaling. And would the magnitude of the signaling also have the same magnitude as would the integrative response? And so I'm going to say the jury's out on that a bit. But we've collected an awful lot of information, a lot of data on magnitude of signaling and how the signals get translated into the integrative hormetic response. So that's how you go about actually developing criteria to evaluate a hormetic dose response. At least I believe.
Okay, in your 2015 article, Model Uncertainty via the Integration of Hormesis and LNT as a Default in Cancer Risk Assessment, at page 3, you write, ionizing radiation was shown to significantly enhance the lifespan of insect model, the confused flower beetle, in an extremely well-designed study that has been repeatedly confirmed. Can you please tell us some details about the experiment and its outcome?
Yeah, this study, it's actually been kind of a classic model. And research that really was conducted at the GE facility, General Electric facility in Schenectady, New York, back in actually 1916, 17, 18, way back when, 100 years ago. In a really unusual study, in which the investigator had pretty strong sophistication in terms of what we kind of know today in terms of variability, design, doses, power, he was so far advanced, and he was able to present very strong evidence supporting of life extension in the huge flower beetle. This finding has been replicated by subsequent generations of radiation biologists, and more or less just confirming and extending with improved, essentially X-ray generating technology, the results. Now, other people got very involved with the longevity issue because it's very significant if you can extend life. And so the insect was a good model in general because they're cheap, their lifespan is very short, and you can learn basic biological principles with them. And so for a long time, the insect model dominated the field of biology. And in fact, when I first went to graduate school back into my PhD program back in 1971, I was actually funded off of a National Science Foundation project that was actually centered around, I'm going to say, aging and using an insect model. So it was very, very common. In today's world, there's competition with all kinds of other biological models, with a lot of work, for example, with nematodes and others trying to find other efficient ways using lots of genetic technologies to try to understand how which genes are playing roles here. But one is able to find that low doses of radiation, low doses of other stressors are able to extend the life of simple, highly complicated living creatures, and they tend to do this within the framework of a hormetic dose-response relationship, being highly supportive of the hormetic dose-response concept. So this is now really reaching a century in terms of its first observation to the very active research that's going on today in terms of trying to extend longevity. So but there are other ways in which hormesis can be fit into extending longevity. For example, in this past January, I had 2 papers accepted on a concept called preconditioning and post-conditioning. And within the radiation world, for the listeners, adaptive response in radiation is kind of equivalent to preconditioning response. It's kind of where you give a low level of a stress, followed a day or 2 later by a very high level of stress, and the initial low dose protects against damage from subsequent higher doses. And when you look at this, you find when you look at preconditioning within an animal model, let's say mouse or rat model, it's very interesting that you find that within the adults, the young adults up to middle-aged adult, you find that the preconditioning is very active and is very efficient in protecting the organism against a wide range of insults. These insults can be induced a stroke, induced a heart attack, damage from shock, lots of different pathologies. But as you get older, at least in the controlled animal studies, the capacity for preconditioning is often lost. And so, but the interesting thing for me, because I tend to study hormesis, is that preconditioning and post-conditioning, they both follow a hormetic dose response. They're manifestations of hormesis. So we've spent quite a bit of time trying to find ways in which you can restore in an older population the capacity for preconditioning. Because I believe once you lose your capacity for preconditioning, let's say me and you, we lose our capacity for preconditioning, that really restricts your capacity to protect your heart, protect your brain when there's hypoxic stress and other matters. And so this is a very significant thing. And could have a major impact on how long we live and how we live, healthy living and how. So in these recent papers, we've come up with 4 or 5 ways by which parent lost capacity for preconditioning can be restored within the elderly body, so to speak. So this is a major area of research. So in this way, hormesis impacts the aging process.
Regarding this, what you just said, what kind of radioisotopes were used? What kind of radiation exposition time of the insect, and what's the extension of the conclusion of your experiment with humans?
Well, the work in humans that's published is typically epidemiological in nature, and tends to support that preconditioning conditioning hormesis is present in the older human being, and that it's actually very dependent upon a couple things. It's dependent upon exercise. Exercise is very important for activating preconditioning activities, and certain types of dietary components can do this. For example, if you take a young mouse or rat that under a normal circumstance would have very efficient preconditioning capacity to resist heart attack, induced stroke, and other things, if you make them either a genetic model that leads to obesity, or make them become very obese relatively quickly, they'll actually lose their capacity to be preconditioned. They actually lose this hormetic benefit. However, if you start them on an exercise regime, it will not take too long for them to regain this. And they can still be just as heavy as they were, but they will have regained their capacity. So if one had to take the choice between losing the weight, so to speak, and exercising, at least in this particular study, it supported doing the exercise, benefit very quickly. So these are areas of very interesting and important public health implications, and this actually fits into any kind of stress. Now, what the stress may be low doses of radiation, the stress may be low levels of non-ionizing radiation, the stress may be heat, the stress may be exercise, the stress may be even psychological stress. Going back to what we talked about earlier in this interview, and that is that the body is not to be seen as a punching bag or an inanimate object that just takes insults. The body actually responds to low-level insults by upregulating adaptive mechanisms that allows the body to respond protectively to future major insults. And if those other major insults do not happen to come, then to use that upregulation for some other type of benefit. And I believe that this is a very significant aspect to the re-educating of the society to realize that our bodies are just not victims of environmental stressors, that actually that we can repair damage, but also we can transform some of those into into upregulated frameworks that can be used to our advantage. And this can be used in medical operations. It can be used in public health. It can be used, just basically your own personal lifestyle if you happen to have that knowledge. So I think this is really very significant, and it really shows the flaw in the philosophy and in the science that undercuts the belief in the LNT framework.
Are there any agent which is not conforming to the hormesis behavior?
Well, that's an interesting question. I would have to tell you that I have a lot of examples in which hormetic dose responses have not been demonstrated in biological systems. I have a folder that's probably 2 inches thick with exceptions to my world, and I believe that these are good studies, and that they show that in those studies that show exceptions to what you do are important to learn from. Now, why doesn't a study show a hormetic dose response? Well, it could be that in fact there's a certain chemical structure specificity that's necessary, and I've seen studies in the pharmacology world whereby you can slightly modify a chemical structure, that organic synthesis people do, and that you may come up with one that is just not biologically active within the framework that you're studying. Change the molecular structure slightly, and it becomes active and hormetic. So there is a chemical structure component to this. Also, there's a situation of hormesis takes place over time. If you don't study it over time, you might miss it, especially if it involves an overcompensation response. My first experience in the hormetic world, I was actually treating plants with a growth inhibitor, and in the first week of the treatment, the plants were dose dependently inhibited. It was a traditional linear dose response, but when I followed it over 5 or 6 weeks, then what I observed was an overcompensation response, and ultimately after the 3 or 4 weeks, a hormetic response emerged. And so in that case, I would have missed it if I stopped the study after 168 hours, but I saw it after 300 hours. And so one has to be aware of, again, this is of the biology of the system and how quickly the system responds to the stress, how the system responds to the stress. So, so even when you do not see the hormetic dose response, it doesn't mean that it might not be there. It means that your study design might not be adequate to detect it. Other times, I think it's very difficult to see hormesis just because the response is so modest. So it's at most it's only 30 to 60% above background, and if you have a highly variable control, or if you get a response that is only 10 or 15%, it may be difficult for you to distinguish this from the control, and the statistical analysis might say that it's not significant, but it may be if you had a larger sample size, more statistical power. But under normal circumstance, there may be just an inadequate power to detect an hormetic type of response. And so there are a lot of reasons why you could have studies that in fact do not show hormesis. And in fact, I can say that there's a lot of debate over let's say radiation and human response to in epidemiologic studies to radiation. It could be cancer effects, it could be beneficial effects, it could be any kind of effect that you're looking at. And I've always been tried to caution myself from getting too excited about human epidemiologic studies, because there's so much variability when it comes to humans. There's also an awful lot that's not known in terms of past exposures, the history of, the genetic background of your parents, grandparents, dietary changes, other things that contribute to variability. And in fact, in the U.S. legal system, you cannot claim causality in a toxic tort case, I understand, unless the odds ratio is at least 2 or greater. So it means that the risk has to go up by double before you can claim a cause and effect relationship. Now, in the case of hormesis, we're only seeing a 30 to 60% increase. We're not even reaching double. And so it's that's why I've been very unexcited about epidemiologic evidence and being useful on a hormetic front. That's why I have put almost all my effort in terms of highly controlled studies with animal models or with cell culture, because you can control the variability very precisely, know their whole history, and make much more accurate judgments. This is why epidemiologic studies are oftentimes, you get a positive study today, the next study comes out and it's negative. Because they're oftentimes looking at very, very small treatment-related effects, and they're very hard to reproduce. Very easy in the old days when people looked at cigarette smoking and smoking 2 packs of cigarettes a day on lung cancer. Very easy to do that. They call that the low-hanging fruit studies. They're so easy to do. But when you get down to studying the effects of 5 cigarettes a day, that's very different than studying 40 cigarettes a day for 20 years. And what kind of sample size do you need to detect the particular effect? It makes it very difficult. And in fact, in the United States, it's very controversial because in the world of what do you call it, particulate matter, where you're looking at very fine epidemiologists are trying to claim biological effects at levels that apparently increase effects by 10%, by 0.1, and none of that would ever be accepted in a court of law, just because of the variability that you have in human systems. So I think, from my point of view, I have tried to control the debate around hormesis, at least my aspect of that be framed within, I believe, highly reproducible experimental protocols in which you can really judge the quality of a biological hypothesis much more acutely and accurately than you can via an epidemiological methodology. Realizing, of course, that epidemiology is very disciplined because it deals with humans and the way people live, but on the other hand, it's in dealing with low-dose effects, epidemiology has very important limits. We have to realize that.
Okay, in your 2013 paper, Hormetic Mechanisms, you list 2 types of agents, endogenous agents and agonists. Can you please tell us the differences?
Yeah, endogenous agents, these are things that are found naturally in the body. Things like cholesterol, things like bilirubin, you might say hydrogen peroxide for that matter. You could lots of different things are found naturally in the body that have things like dopamine, adrenaline, noradrenaline, many things. And they actually, all the ones that I just mentioned, they all have hormetic dose responses, and I've probably written papers on all these as individual compounds. And there would be individual endogenous agonists who have naturally designed functions, so to speak. They're mediated in many cases through hormetic dose responses. Exogenous are the things you take into your body. It could be the medications that you take in, the food stuff from the foods that you eat, or the exposures that you have from your workplace or hobbies. So that would be a difference. But in general, it still doesn't make a lot of difference. You will get hormetic effects induced whether the agent is a endogenous agonist or a exogenous applied to a system. If it stresses the system, you're going to induce a hormetic response. You can be pretty well guaranteed that's going to happen. Endogenously, I would say every single system in the body that I know operates through biphasic dose responses, and they operate through through agonist concentration gradients. And so it's kind of, you have to think of it as a signaling system, and that is that when you attract an immune system to a location, you do this in different ways, but they tend to follow concentration gradients. If the concentration is in a low dose, they may be attracted. If it's too high, it tells them to go back. If you are, and it sounds strange when you are growing new capillaries, new blood vessels. These blood vessels are circular, so they can carry blood. How do you grow curvatures? You can grow curvatures through the manipulation of concentration gradients, and we've had papers published on that, in which one side of a biological plane has a low concentration and it speeds up cell proliferation. The other has a higher concentration and it slows it down. And over time, you get a more growing on one side and less on the other, and eventually you get a curvature. And it's the way the capillaries grow, the way eyes grow, the way the head of the femur grows. Our body is made up of a lot of curvatures, but the body has found ways to use concentration gradients acting via hormetic dose-response relationship to facilitate these processes. So most people think of hormesis as just an adaptive response to stress, but it's much more than that. It's much more fundamental to the biological workings of all systems.
What could the future implications of the adoption of the hormetic model be?
Well, see, what I think we're confronted in today's world by political realities. And the political reality is that people who have adopted the LNT don't want to give it up because of either they don't want to admit that they're wrong, or they just are very fearful. I mean, put it that way. And the hormetic situation is that the data is clearly supporting hormesis much stronger and stronger every single year. It's not going to go away. The data are what the data are. And what I've tried to do is made several papers published in 2015 and 16 on the hormetic model uncertainty. What I've tried to do is to find a vehicle for dialoguing with the LNT group and the hormesis group in a way that is constructive. And so I said, well, let's put them both together, and we can see. And what I found was that this is actually interesting. When you calculate using animal studies as the framework, but when you use an animal risk assessment model framework, you find that at the dose at which the animal is projected to have a 10 to the minus 4 cancer risk happened to be at the nadir, or the lowest point, of the hormetic dose response prediction. So what that really meant was, well, if you want to optimize the benefit, then you want to choose the nadir of the hormetic dose response. Okay, and how bad that could it be if, let's say, hormesis is wrong and the agent acted via a linear dose response, which I don't think would be very possible. Let's say, in this case, perspective. That would mean that in fact, the worst you would have would be a cancer risk of 10 to the minus 4, which is 1 in 10,000, which you can't measure anyways epidemiologically. You don't even know if it's real. The hormetic dose response would actually give you a tremendous benefit in terms of a reduction in tumors and background tumors. And so my sense of it is that really going forward, regulatory agencies living in a political world, I believe that the vehicle that they should consider is the model uncertainty vehicle, in which you incorporate LNT and hormesis, in which the optimal value that you are choosing is at the hormetic nadir, and I believe that politicians and others could live with a maximum risk of 10 to the minus 4, even though it's incredibly unlikely. And that's way they would not be giving up the benefit of the hormetic dose response. What they would have to recognize is that they would have to go from a 10 to the minus 6 up to a 10 to the minus 4. It would mean that the cleanup levels and exposure levels would increase by approximately 2 orders of magnitude. This may freak out people who believe in lower is always better, but actually the science is supporting that we should strive for the nadir of the hormetic dose response, and at that hormetic response will not be greater than 10 to the minus 4, which the advocates of LNT could not even find if they were the most powerful of epidemiologic studies, could not detect that change. So I think it's moving towards compromise, towards dialogue, and towards integrating of a model uncertainty in public policy. And I believe that hormesis is going to be at the center of that discussion.
I want an opinion on what you just said, your opinion, which is basically what's convenient for this group to be stuck to a certain model, like the LNT model. What's convenient for them to be stuck in that kind of model?
I think what's convenient and what's practical, and that is that I think it's probably economic. Mm-hmm. That is that you don't want to eliminate technologies, and you don't want to eliminate diagnoses of patients that need to be diagnosed if they might have a kidney disorder, and you don't want to hold back a CT scan, things of this nature that could save somebody's life. You want to have reasonable cleanup levels for environmental sites. My approach also, if any country has to deal with the implications of a dirty bomb, this has a lot of features to it, because ultimately, if a dirty bomb was released in a large city somewhere in the world, everybody would be going crazy, be hysteria, and thinking that the world was coming to an end, and it's most likely far from true. And this integrative model would allow cities to function, and actually probably be in a much better health zone than they were before it. But if you look at the models, I mean, you have to see what every specific situation is. But my sense of it is that it allows politicians more flexibility in terms of the range of economic options, response to terrorism, adoption of technology. I think that this is just better, and it's also more scientifically founded than the alternative, which is the LNT model, which only leads to hysteria, doesn't lead to good science, actually is poor economically, and is politically crippling. And to me, it makes no sense for any intelligent form of government to continue to embrace LNT and to think it's doing something good for its people.
What are the goals of the research in the hormesis area?
It's actually, the problem with hormesis is that there have never been goals in this area. We have put together the entire hormetic argument in the last 20 years on the basis of luck and by studying what people have done and where they've inadvertently discovered hormesis. What I would look for the creation of hormesis research centers across the world, in which they could be pharmacologically oriented, or radiation oriented, or environmentally oriented, evolutionarily oriented. We've never had a focused framework in a broad sense on hormesis. Hormesis is actually, the many thousands of examples I've found have been really found by accident. For the most part, there are now some prospective studies, a lot of prospective studies going forward, but actually there's been no real strategic research plan that has been motivated by the hormesis assumption, and that really needs to change. Major governmental research entities need to address this, and until they do, the pace of improvement will not go fast enough. So that's, to me, it's you really have to have some vision and some courage within these federal agencies to say, this area needs investment, and it's interesting in terms of, like me, for example. I'm the center of a lot of controversy at different times, and people always try to say, well, let's follow the money trail. Who's funding you, and what private sectors are funding you? And it's industry's best interest to fund people who are supportive of hormesis. And so what I actually say to these people, I actually look at the many hundreds of studies that are published on hormesis every year, and I look for their funding sources, and I don't see big industry funding these at all. Very few. These discoveries that are made are inadvertent off of their government grants that they have. There's not the big pharmaceutical, the big chemical company. They've been afraid to get involved with this because of being tainted by governmental judgments and other political judgments on them. And so there actually has been, as far as I can tell, no major investment in hormesis research, certainly in the United States, by I'm going to say by the private sector. It has not been done, and this actually needs to change, but not just by the private sector. It needs to be done by the public sector, because hormesis is in the public interest to know more, from preconditioning to all other sorts of adaptations and the like. And so I think that this is it needs new effective leadership, which has it just needs leadership. There's never been leadership on this as far as major entities such as the NIH, such as the EPA, such as others, and the European community. It's got to be the same as well. In Japan, actually, there was a lot of funding by the electric power research, and published a lot of outstanding work by Japanese biomedical investigators on low levels of ionizing radiation, inducing all sorts of adaptive responses that had all kinds of medical implications for improving therapies for diabetes, improving therapies for various types of neurological conditions, and reducing cancer occurrences and the like. The Japanese have done remarkably excellent research, and their work, for the most part, is always quietly published in very good journals, and never strongly enough appreciated for the quality and its significance that it has.
Are these studies a consequence of what happened in Fukushima, or they are totally independent?
It's occurred independent of Fukushima, and actually started after 1985. So
Okay.
it had a good 20-year run, you know, that sort of thing, even more than that. But yeah, and it really came about as a result of leadership within the Japanese electrical power research industry, and they had a nice link up with the U.S. Electric Power Research Institute. But the Japanese took the main lead in terms of funding hormesis-related research, and they, more than anyone in the world. But the Japanese are also more less showy, less ostentatious. They publish quietly, and as I said, they do excellent work. If it was, you know, probably, you know, with the showmanship that comes from, you know, scientists in the United States, there'd be so much self-promotion of the research and the research quality. It'd be much more widely known. But yet, the Japanese work has been extremely substantive and high quality, and really, people should really take a good hard look at it because it's excellent.
How could humanity benefit from the exposure to ionizing radiations conform to the hormetic model?
Well, I think that hormesis has a lot of potential for use within the strategy for biomedical treatments, therapeutic treatments. I'm thinking of a lot of usage tied into the concept of preconditioning, and how we could use this to protect people against the large doses of radiation that are used in cancer treatments. So, say for example, if you have to undergo a very large cancer, you know, large exposure for tumor treatment, there needs to be ways to protect tissues that you don't want damaged, and you can do this perhaps through some type of preconditioning protocol that may not involve ionizing radiation, or it may involve ionizing radiation. There are ways in which one could make therapies much more effective than what they are. We tend not to think long term, or the healthcare system around the world doesn't anticipate this. But for example, you could protect people who are very vulnerable, who are going to have surgeries, by preconditioning them before they have their surgery. You could post-condition them after they have their surgery. There are so many different things that could be done in terms of using this knowledge today to impact human populations. Also, not just human populations, impacting plant productivity and other kinds of entities that we're interested in. And so I think that you may also be able to better type people to find, you know, there's a lot of variability within human populations, so there may be some biomarker research that needs to be done to identify and screen people and type people as to you know, where their optimal zone is for a hormetic response. And your zone may be different than my zone, and not one dose fits all. And we have to recognize that there is a lot of variability, and that our optimal dose may change as we age, or other. So I think that knowledge of the basics of how hormesis works, in different agents that induce it, including radiation, this is still pretty much a black box, and we are our role, my generation, is more or less challenging the scientific community and the funding community to take this seriously, because, you know, we're really talking about not an answer today. We're really talking about an answer in 100 years. You might. It sounds. I mean, we're long gone, but it's your kids, that will be benefiting from this. I mean, humanity is not going to die out in 2020. In 2120, people are going to be here, and they'll look back on us, and they'll see what we did to move it forward. We're just moving it down the road, so to speak. But these are, when you look back to Hugo Schultz in 1880, and he starts his hormetic research. Well, it's not just 1980; it's now almost 2020, and all this moves ahead, and so I'd hate to have 2120 come by and we're still talking about the same problems. It really needs to move far beyond this, and it needs, if nothing else, major investments in research are needed to better understand this, so that the good decisions can be made at the population and at the personal level. Okay.
So, which radioisotope do you think could be more indicated in order to pursue the objectives you mentioned in your previous answers?
Yeah, I don't think it's going to make any difference. I think that radioisotopes, it may make a difference in the particular tissue that you're studying, but radioisotopes, as well as other sources of ionizing radiation, will have biological effects. Their effects will be very dose dependent. They can induce a variety of hormetic types of dose responses. They can upregulate these adaptive mechanisms. And I think that specific studies have been reported, whether it's been with radium or plutonium or other ones, that you find the biological system, you can find hormetic responses that have been reported in strong studies with these. Whether the effects will be, if you use them, how you use them, what's the ideal way to go forward. These are questions that people who work in them on a daily basis have to address. My view is that they're all capable of finding resonance within a hormetic framework, and there's evidence to support that. But what the overall strategy is for their use and how it fits in, that would be for specific experts in those areas.
Professor Calabrese, thanks very much for your time and for being with us.
Hey, thank you very much, Carlo, and appreciate it.